Morgan, so in the last question, what I want you to do is determine the current in terms of R1, R2, R3, and R4, and the power supply voltage. So yeah, it's going to look a little messy. It's your only theory question really of the lab, so. Does that answer your question? Right, but I mean, you need to calculate the total current. I mean, yet you need when you you need to derive an expression for the voltage across R1 in terms of all the given quantities. Well, what you're given is this, right? You can certainly calculate the current through your circuit, right? You can calculate IS. IS is going to be what? Delta V over the equivalent resistance. Right? And then I can derive an expression for the current through this way. Let me check something out real quick. I forgot the ammeter. Well, you can derive an expression for this, right? And you know this circuit is the same as we can combine these two. These two are in parallel, right? I did that wrong, didn't I? And so it's an IS then. Oh, I'm sorry. I've been using the other camera, so it always changes things on me. Is that better? Okay. So, you agree with this is the total current in the circuit? So then, the voltage across this guy is going to be this times that, right? Hold on, let me move the chat box so that I can see the whole chat box. So this times this is the voltage across this guy. Then I take that mess and divide by R1. That's it. So isn't it true that I got into the R1, R2, R3, R4, the power supply voltage? It's going to be a mess, so. But that's really all I'm asking for. Even though it's a little messy. Yeah, that's what I was saying, right? I do it in terms of all the resistor values and the power supply voltage. That's what I said. Okay. I mean, the rest of it's easy now because I just said take this times this, that'll give you the voltage across that. And then I divide that expression by R1, done. Of course, you might have to simplify a little bit, but I don't know how much simplification there is. Okay, so I graded the Ohm's Law lab, and so I have a few things I want to say. And I typically I make comments after a written lab. There's only 4 written labs this semester, so we're talking about. So see, you're talking about lab 4, right? Okay, let me get to that. I'll get to that. Okay. Let me talk about my comments for lab 3, then we'll talk about lab 4. By the way, the sound quality might not be as good in this lecture because I'm running 2 cameras today. Because I need to show you the electric motor. So you guys can hear me okay, right? So the quality might not be as good. The quality of the video might not be as good in terms of the sound. So I noticed a couple of things, and probably because you don't remember some things from maybe the previous semester, I'm not sure. But when you're asked to plot voltage versus current, what this means is you're plotting Y versus X. This is Y, that's X. So your graph then should be voltage here and I here. And then slope is R. And what a lot of people did was they did this. But in this case, 1 over R, or 1 over the slope, which I'll call M, is R. So I can tell right away, because the resistor value, when you measured it with the multimeter, was less than 1,000 ohms. And when you did this, a lot of people made this graph and quoted R, it was over 1,000 ohms. So your quote was incorrect because you forgot to take 1 over the slope. You gotta look at the units. I think there was like one person who made the correction, but not everything was correct about it. I think one person correctly showed that R was 1 over the slope. Most other people, they made this graph and said the resistance was equal to the slope, which is wrong. So when you plotted it backwards, I took out points because I know that your analysis is not correct. Yeah, I understand that, but it specifically said in the graph to plot current, voltage versus current. And the reason why you do that is because of the fact that you get the slope right away. So, but if this is okay, but how do you get delta R? I mean, if you're able to do this correctly, if you're going to do this correctly, then you have to get delta R correct too. If R is 1 over the slope, then what's delta R? You can't say it's delta M. This is a function. R is related to 1 over the slope. You can't just, and what some people did was they said, oh, delta R is the uncertainty in the slope. And that's not true. You got to do error propagation. To define delta R from this, you got to take the derivative of R with respect to the slope. And I'm going to take the absolute value of this because I got to take this, I got to square it and take the square root, okay? Which is the same thing as this. That's the uncertainty in R. Now, it could be that you got lucky that you got the same value. It's because R was near a kiloohm. But I'm not sure that you understood that you had to do this to calculate that because you didn't show the work. Okay. So this was not done. I don't think nobody did this. Or at least they didn't show any evidence that they did that. So you got to be careful. Okay. When someone says plot this versus this, y versus, and I understand your question, Robert. We varied v to measure I. And you're right. It should really be plotted the other way, but then more work to extract the information. This is why we specifically said to plot it this way. And if you notice in the last part, the part we skipped, we actually plot I versus V. Okay. Another thing, I saw this a couple times. Now, we know the graph is going to be linear for Ohm's law. A straight line. And some people plotted this. And I say don't do that. Why? I say plot this. Do a fit to this function. Why do I say that? Why would I say use the second one, not the first one? Yeah, you don't want to assume that the y-intercept is 0. And yeah, you can correct from some source of error, systematic error. You do this, you're forcing the graph through the origin. So don't ever use this for a linear graph. Use this. Don't ever force your graph to go through the origin. Yeah, and that's a good question. The battery does have some internal resistance, right? So you always want to use this for a graph. You always want to include something where it has a y-intercept. And if it's 0 or close to 0, well, this value will be close to 0. Okay? Now the next thing, some people were using the new version of graphical analysis. And I'm going to say don't use it. The new version of graphical analysis that's online, they say it's free and stuff like that. Don't use it. But don't use the new version of graphical analysis. Why? It doesn't show the uncertainties in your curve fits. I'm going to write it down so when you see the video. Okay, so don't use the new version of graphical analysis. Some folks, when they make the graph, here's a piece of paper. Okay, this is the sheet of your lab report, and they make the graph maybe like this. Well, my question is, why do you want to make the graph so tiny? Especially for an older person like me, hard to see. Okay. Although the people who did make the graph tiny, they actually made the font big. Some of the folks who made the graph big made the font tiny. So if I make a graph, I should make it a decent size. And of course, I should label the axes. So if I write the axes like this, can you see those letters? Can you see what I wrote? Can anybody see that letter? No. Okay, so don't do that for your graphs. Okay, because people did that for their graphs. Okay, you don't want me to write this small on the board, right? Don't write that small on your graphs. So the font that you have on your axes should be the same size as the font that's in the text. Okay? I don't want to have to magnify that everything all the time. It should be the right size so that if you print it out, you can read it. You know, I don't need just gargantuan font, but I don't want font where I need a magnifying glass when I print it out. Okay? So don't make your font too small. And part of this is learning how to make a presentation for somebody else. A lot of times we write a lab report, we don't think of the audience, we're writing it to ourselves. And you got to think about writing this to an audience. That's very difficult to do, I know. Okay? That's something I always got to think about when I write up labs for you guys. I got to think I'm writing to you guys, not to me. It's hard. But at least the part where you allow somebody to see something, that's important. So don't make things look clean. So I saw a couple of those instances. By the way, normally my labs are with 20 points. I actually made a lot of labs with 40 points. And the reason why, so if I find little things that should be changed, I can take off a little bit of points and really not affect your grade too much, but that tells you that you should correct that. Okay? Because in the past, I would see those things and I'd take off points, and then people do the same thing over and over again. And when you take off points, people respond. Okay. And I don't take points off of this, but this is just word choice. So when you're asked a question in a science lab, and you answer it the following way. You start out, I believe, or in my opinion. What else? I think. This one's not as bad. Maybe I'll say I feel. When you answer a question, you don't want to start out with like this. This is a science class. This looks like something maybe involving a political discourse. Okay. When you're asked a question in a science class, or you're writing something up for science or engineering, you should say, the evidence suggests that. And granted, you are making a judgment, but you're making the judgment based on evidence. So you want to say it that way. So it sounds like you're making a statement based on evidence. But if you just say, I believe that, and then make a statement, number one, sounds like you're dictating to someone what you think is happening. That's what politicians do. Okay, you shouldn't be doing that. You should say, the evidence indicates that, and you really shouldn't say shows that, unless it's extremely clear. Just say the evidence indicates that, because usually what happens is you need to have somebody else corroborate. Okay. Look at the evidence suggests that, and then you answer your question. Okay, because you really don't want, in science, you don't want to say things like this. I really think scientists should avoid using these terms, especially nowadays where everything's based on what they believe, not what really. They don't base things on fact. They only base things on what they believe. Okay, especially with our political climate nowadays, you really should focus on saying things in terms of what you evidence. Okay, and try to avoid saying things this way. That's just if you're taking philosophy or some other class, then yeah, you probably should say things this way. Okay. Coding uncertainties. So, problem came up regarding uncertainties. Our multimeters are a little strange because the precision of the multimeter is higher, quite a bit higher, than the accuracy of the multimeter. And so a lot of students, when they're doing the calculations, they're calculating the uncertainties. So they measure V. So they get, let's say the VR1 is 2.71 plus. They probably get something like this. Because the meter gives you the value of the decimal place. And you look up the accuracy, and the accuracy tells you that to this decimal place, then there's something weird about that. Okay. Now for this lab, we're just going to go with what we did. Okay. But I think in the last two labs we write up, the uncertainty that we quote for our measurements should really be based on what the manual says. So for example, if you measure resistance of 100 ohms on the 200 ohm scale, I think the manual says that the accuracy is this. Which means the digit after the least significant figures of 5 is out by 5. So what this means is your uncertainty is 0.4 plus or minus 0.05 ohms. It doesn't make sense. So this could be 0.45 or this could be 0.35. But I'm just going to quote it as 0.4 because I'm just going to quote it as 0.4 ohms because we, in our class, quote our uncertainties to one decimal place. So it basically would go by this number. So in the last two written labs we do, so see, this is, I guess, goes to your question. We'll use what's in the manual to report our uncertainty in all of our measurements. But for this lab, whether you use the last digit or the manual, that's fine. As long as you do the error propagation correctly, I'll be happy. And that's one thing that's my fault. I didn't think right off the top of my head, I didn't think of right away was that these multimeters, the number of digit it displays is too many as compared to the accuracy. That's really shouldn't happen. Because these are not the most expensive multimeters, but they're pretty good. To see this, does that kind of answer your question regarding uncertainties? Well, you quote it to one, you quote the uncertainty to one digit, right? For question 3 in part 2. Okay. So, since you're asking now, I guess, you can use, so the measured value of IC, you can look at the manual and see what the accuracy is and use that as the uncertainty. And then the calculated value, from error propagation is this, remember, right? Because delta IC or IAC was I1 minus I3. And then use error propagation. If you use error propagation, this is the expression you get for the uncertainty. But of course, you calculated these, right? And then from the IAC measure, you can use the value from the manual. Yeah, you should, right? Because you want to present evidence for your answer. So you need to measure. You need to mention the uncertainties. Are you talking about during the calculation or answering question 3? Okay, so when you're doing a calculation for IAC, you will have calculated these already. So you're going to put these into the equation. You want to show your work, right? Did I answer your question? Maybe I'm not clear on your question. Yes, you're doing the same as what you did in part 1. You're showing your work. You mean for I1 and I3? You get uncertainty in I1 and I3. You're going to calculate them separately, but you only show your work from one of them. So let me go to the. Let me change the view so I want to share a different document. Hold on a second. So let me go through the process. Let me change. Let me go to the other lab. So in this table, you're going to calculate IR1 and this uncertainty, IR2 and this uncertainty, IR3 and this uncertainty, and IR4 and this uncertainty. So you're going to calculate all those. You can show your work for one of them. Then you're going to calculate this, show your work for finding IAC and the uncertainty. Okay, so you can show it below. And then when you come and answer this question, you can refer to the answer to what you have. Where'd it go? Up here. Does that make sense? So you're going to calculate this and show your work here. And you're going to show one of the sample calculations for I and this uncertainty. And when you quote this one, this is going to be, where's it? I'm sorry, I did it wrong. This one's going to be calculated. So you're going to show your work here. This one is going to be determined from the multimeter. So let's say you get 3.59 I'm just making numbers up, okay? Let's say you get that, and this comes from the multimeter. And then you get a value here. This value in red, you calculate. Okay. Okay. Yeah, you just need to show this once so that I understand that you know what you're doing. So you just got to show the equations and then the number plugged in, because then I'm going to assume you're going to do the same thing for each of the subsequent calculations. I don't want you to do the same thing over and over again. Okay. So I want to talk about the new lab. It's really more like a project. It's the motor. I call it the motor lab or the motor project. So this is due November 25th. Okay. You're going to be building a motor for this project. And the motor is not hard to build. I mean, you're given in your lab kit, there is a motor kit. Let me switch views. In your lab kit, there's a motor kit. Okay, it comes in a bag like this. That bag has a hole in it, so I can drop things. So you have your board. This is the base of the motor. You have the magnet wire. Be careful with the magnet wire. It's expensive. Let us know if you have problems with the magnet wire. This is very expensive. Last year, somebody tried to order it because they kind of messed up, but you tried to order it through Amazon. It was during the height of COVID, so it took forever to get it. So she just had to come to us and get it. And then you have some nails. And you'll have a compass. I actually have a magnet, but you have a compass. And then you have instructions. The instructions are also in the lab, too. You have instructions on how to build it. Yeah, this is magnet wire. It's copper wire, and it has an enamel coating on it. And the reason why you want to have the enamel coating on it is because it makes this thinner. So when you wrap it, you don't have just a thick wrapping, because the coating on it usually is quite thick when you put like an insulator over it. So this makes it real thin, and it makes it easy to bend. Okay. But of course, the enamel melts. If you put too much current in this thing, you will melt the enamel. And then you need more magnet wire, because you're going to short things. And I forget how many feet this is. I think it's 30 feet of wire, if I remember correctly. So you're going to build something. So I'm going to switch cameras. So part of the reason why the sound quality is not good, because I'm using the second camera. So let me switch cameras. And you're going to build something that looks like this. Okay, when all's said and done, this is a student that just basically built a simple motor. Just went by the instructions. Okay, I'm covering up the name of the student. But this student got this motor to run at 1.12 volts. So you're going to be graded in terms of the voltage that's required to run this thing. Okay? So let me go back and go to the document. Let me go to the last page of the document. Actually, the second last page. So you're going to be graded on the following. If your motor runs on the 2 batteries we gave you or less, you get 30 out of 30 points. But then there's also 10 more points based on you answering these questions. So you got to answer these questions too. So each one of those questions is worth 2 points. And they're pretty straightforward questions. Just answer them. Just answer them carefully. Don't answer them in terms of the motor you built. Okay, relate the answer to your questions to the motor you built. So it should be, getting these 10 points should be straightforward. And just get you go through the concepts involved with the motor. Last semester, most people got it to work with 6 volts or less. Normally, when we do this on campus, you have to get it to work at 2 volts or less. The reason being, we have testing equipment. We basically have a big power supply we can have you test them on. And we can get, we can see what the heck's wrong. And then you'll also have our help, either me or Tyler or anybody else who's around, to help you to get it run. But we had several students last semester to get it run on one battery. Okay, which is 1.5 volts. So you should be able to get it done working at 1.5 volts. Okay, a lot of you folks should be able to. Normally, this is especially for the engineering students, this is a fun lab because they get to build something and make it work. I see this as a lab where you kind of learn how to troubleshoot things. Because building, wrapping wire and stuff like that is not going to be too hard. There's a couple of requirements you have to meet, but you can wrap wire, let's say, to build your armature while you're watching TV, okay? I don't know if there's anything good on TV right now, but you can watch TV and build this armature. You have to, it's very important though when you wrap the armature that you wrap it so that you minimize the moment of inertia of the armature. You want to get nice symmetry and nice, a nice tight wrapping. And this one was actually good enough so they would run at 1.12 volts. Okay, sometimes you just get a big ball of wrapped wire and that's not going to work very well. Okay. So building is going to be not too bad. Oh yeah, by the way, you're going to need hammers. A hammer to nail things into the board. Okay. But most of the issues are going to be you troubleshooting. And troubleshooting is an important skill. Even though you're not going to be an engineer, not everyone here is going to be an engineer. Some of you guys are going to be computer science majors. Some of you are going to be chem majors. Whatever you do, whatever field you're in, you have to learn how to troubleshoot. That's a really important skill. Whether you're building something for engineering, whether you're a chemist and you're designing an experiment, trying to make it work, whether you're a computer scientist writing code, something will go wrong and you're going to have to make it work. So you got to figure out what's wrong. And so what we try to do is help you develop a thought process that maybe you would need in your field to troubleshoot. Okay, you start with the simplest things and then and use a process of elimination. Okay, so you're going to ask questions about why isn't my motor working, things like that. I did create a discussion board with an FAQ on it so that it'll give you a start. Okay. Things that you need to concern yourself with, again, making sure that this is wrapped nicely. In fact, I would build this first. In fact, the instructions tell you to build this first. And by the way, you need a minimum number of 2 nails to make your armature. All right. The armature must be must consist of no less than 2 2.5-inch nails or a rod or dowel that is 0.25 inches in diameter. Of course, the rod has to be magnetic. You are allowed to use bearings. So let me show you one that has bearings. Although this one didn't work as well because I think it was too heavy. And I'm going to try to cover the name too. Okay, this one actually was built with bearings. This didn't work as well. And if you look at the electromagnet is beautifully wrapped, but the armature is not. A little bit more messy than the other one. And then there's a lot of weight here. There's quite a bit of weight here. Okay, so this one worked at like 5 volts or 5.6 volts, whereas this real simple one worked at 1.12 volts. I don't know if you can see the writing there. Okay. So that's one of the issues. The other one, and probably the biggest issue, is this: your commutator. Okay, so this student, when they built the commutator, they used copper tape. And you're allowed to use copper tape. This actually works better. If you look at the instructions for building the commutator, they just have you take the magnet wire and just wrap it around. It works okay, but copper tape works better. You notice that you have the splitting, the separation of the two pieces of the commutator. Okay. If you don't get good contact, it's going to require you to run the motor at a higher voltage. Now, as you run the motor at a higher voltage, you're going to run more current through your motor, which means your wires are going to get hotter. So be careful. But really, it doesn't become an issue until you get about 9 volts or higher. Okay, it starts to become an issue when you're get above 9 volts. So try to stay below 9 volts. Oh yeah, the other thing too is your armature and your electromagnet have to be connected in series. I'm sorry, not parallel. That makes it a little bit more doable, because otherwise you might melt the coating on your motor. So everything has to be hooked up in series. So this contact, the contact between the brush and the commutator, is a big issue. If you don't have good contact or consistent contact as this thing spins, it's gonna require higher voltage. And so that's one of the biggest issues that we have in this lab. And one of the ways to test it is to connect the battery to it and an ammeter and measure the current. You got to be on a 10 amp scale, by the way. And just spin this thing slowly and watch the current reading. If the current reading varies greatly, that means you don't have really good contact. And that's probably why you're having a hard time getting it to run at a lower voltage. So what you can do with your brushes is maybe try to use what this guy did. He used stiff wires for the brushes. I mean, this is a really simple motor, and you're working only at 1.12 volts. There's a lot of little things you can do to make this thing run well. Let me show you the close-up of the motor I showed you last week, because last week I didn't have this camera. Let me pull up the motor. There's that thing something. Now, I am doing something that's not allowed for your lab, but I did hook up everything in parallel, and I did it because it's just easy to do. Okay, so here's the electric motor, the demonstration one. I'm going to take out one of the brushes, and when you look at this is the commutator. You see the splitting there. So as a hint, you want to make sure that the current reverses directions when the torque on the armature is 0. You do not want the current to reverse direction when the torque is maximized. Okay? So that's another issue that can come up. All right, so let me turn this on. This is going to run at, let me make sure I have my, we got disconnected, so let me reconnect this. Okay, there it goes. And so right now it's running on 5 volts, so it's gonna go really fast in a second. It's still accelerating. That might be a little bit too fast. Let me turn down the voltage. So this thing, and this heavy, is running on 4 volts, but of course I'm using a lot of current. Because I have everything hooked up in parallel. I'll probably need double the voltage if I hook up everything in series. Maybe more than double the voltage. And I also have a lot of friction in this thing. Okay, let me turn that off. So again, these are the brushes. This is the commutator. This is the armature. And this is the electromagnet right there. This is the electromagnet. Do you folks have any questions regarding this lab? No questions? And again, be aware, I cheated. I hooked this up in parallel. These go to the same power supply, which is on the floor. But you're going to be forced to do everything in series. No questions? Concerns? I hope you have fun with this. Of course, I'm always going to have 1 or 2 students who are not engineering majors who are not going to be happy doing this, but it's really not that bad a project. Okay, so if you don't have any questions, again, this is due November 25th. And all you have to do, I guess, is submit a video clearly showing the wiring of the motor, spinning, the motor spinning on its own. It shows that the operating voltage, basically showing me how you powered it. And you got to write your name on the wooden block. Okay. Don't make a long video. You know, maybe 15 to 30 seconds. That's it. So, see, you didn't get the 2 D-cell batteries. They're not in your kit. Okay, so if you didn't get the D-cell batteries, you might want to contact Tyler, if you can. He's usually there on Thursday, so Wednesday and Thursday. So contact him today, and maybe he can arrange for you to get them. Otherwise, you can just buy them. The D-cell batteries cost, I mean, they're not super cheap. They might cost you $6, $7. It's up to you. You can contact Tyler. Okay. Yeah, you know, it just depends if you're willing to drive to campus and pick them up. Okay. And the thing is if you need more voltage, then you're going to have to get more. You're going to have to buy some more batteries too. Okay. We gave you 2 because that's what we want you to run it at. But if you need more, then you're going to have to get some. Now, last semester, some folks tried to use 9-volt transistor battery. They have a high internal resistance, so that it's not going to work. These have a lower internal resistance, so you can actually it can actually supply a lot more current. Okay. Yeah, you should all have a 2 D-cell batteries. If you don't, please ask Tyler. And if you email him and you haven't heard from him, just let me know. Okay. All right. Since they're D-cell batteries, you can always purchase them if you want. The motor kit, you're not returning anyway. All right. You're not gonna when you return the lab kits, By the way, as a reminder, I created the last lab. The last lab is return the lab kits. You don't need to return the motor. So the motor is for you to keep. So if you want to, you can just buy your own batteries. It's up to you. Okay. Anything else? So in the remaining 17, 18 minutes, I want to start at least talking about chapter 31. I'm hoping I get as far as I did with the other class. Just give me a second here. So before I show you let me just show you the PowerPoint notes real quick, and I'm going to have to switch again. So we're going to be looking at Faraday's Law, which I think is probably the most interesting chapter in the course because of the number of applications in real life of these ideas. So I'm going to remove my motor. I'm going to set up another demo real quick. All right. So chapter 31 to me is an interesting chapter. So I have a demo I want to start with. I have here, I have a device called a galvanometer to detect current, and the biggest current it can detect is 2 milliamps. So a full deflection of 2 is 2 milliamps. And I have 3 coils. The coils are all connected to the galvanometer. And what I'm going to do is take this magnet, and I put a strong magnet at the end. These little things are pretty strong magnets. Okay, if you get 2 of these, put them together, they're real hard to pull apart. And I'm going to run it into the coil. Look what happens when I run into the coil. The needle deflects. So by me running the magnet through the coil, I actually have a current. I'm actually making the electrons move. And if I have more turns in the coil, I get an even bigger deflection. And notice the direction in which I move it makes a difference, because if I move it in, the needle moves in one direction. When I pull it out, the needle moves in the other direction. And if I just leave it if I leave the magnet inside the coil without it moving, nothing happens. It's only when it's moving. The coil is experiencing a changing magnetic field. All right? The coil is experiencing a changing magnetic field. So there are electrons that are moving as a result of me moving the magnet. So there's energy in that coil. Where's the energy coming from? If the electrons are moving in the coil, it means they have energy. Where did energy come from? Can't come from anywhere. Where do the electrons get their energy? What do you think? Well, it came from me, right? I did the work. I'm doing the work. I'm putting the magnet in and out. So I'm doing the work. Okay? So the energy came from me. So that means the electrons are moving in this thing. So I actually have, in a closed loop, in order for me to have a current, I have an electric field. Is there a force working against my movement? That's a great question. Yeah, there is. I mean, the force is small, but it's there. And on Monday, we're going to do this particular problem and answer your question about the force against my movement. That's a really a great question. That, in fact, that force has to be there to conserve energy. So Morgan, we're going to go through that in detail on Monday. I'm going to go through a simple example and carry it all the way through in gory details. It's actually a simple example, but I'm going to go through all the physics on it. So in this coil, there's an electric field. That's how you're going to get the electrons to move, right? There's going to be electric field in the coil. But when I integrate the electric field around the closed loop, I don't get zero. So the integral around the closed loop is not zero. Because remember when we do Kirchhoff's law problems, the integral of the electric field around the closed loop is zero. So there's something different, characteristically different about this electric field as opposed to the electric field produced by a battery. This electric field is not conservative because the integral around a closed loop is not zero. And in fact, the electric field circulates parallel to the loop. This electric field forms circles. The closed loop is just this loop. Well, there's a lot of turns in the loop. So, right, there's a loop of wire. In fact, there's a lot of loops of wire. We're just talking about one circle, or we can talk about n circles. Is that okay, Morgan? The loop is just a loop of wire. There's the closed path produced by the wire. So somebody asked some interesting questions today. Said, well, what if what if you actually take this magnet and just move it outside of the loop? What does it do? Now, of course, my hand is moving. My right hand is moving, so this thing shakes a little bit. But what happens when I move it outside the loop? Nothing. He was asking, does it have to be inside the loop? And the answer is yes. And I'm talking about these loops formed by the wires. The magnetic field has to penetrate the surface formed by these loops of wires. If the magnetic field does not penetrate the surface enclosed by the wires, you're not going to get an induced voltage. You're not going to get a current. Okay. So let's take a look at our PowerPoint notes. So this is essentially what I was demonstrating when you run the magnetic field in or out of the loop. So this might make it clear, Morgan, what the closed loop is. It's just a closed path for the electrons. Same thing as when you look at a loop when you use Kirchhoff's laws. Yeah, I mean, it is. I mean, we're talking about this entire loop, I guess. And the magnetic field is penetrating the main area. I can, these two wires, I can put them really close together so that all the area is over here. But that magnet has to penetrate that surface in order for the galvanometer to deflect. It's just a circuit loop. That's really all I'm referring to. The loop of a circuit. But the magnet has to the magnetic field has to penetrate some surface enclosed by the loop. So even if it penetrated here, you would get an induced EMF. It'd probably be small. Okay. So our loop behaves as if there's some source of EMF connected to it, even though there isn't. That's why we call it an induced EMF. And if the magnetic field changes, then you have an induced current, along with the induced EMF. And one thing I notice is that the induced current will be, if I move the magnet through the wire, the induced current is going to depend on how fast I move the magnet in and out of the loop, and in what direction I move the magnet in and out of the loop. And whether I move the north pole of the magnet into the coil or I move the coil towards the magnet, I really get the same induced EMF. And that's a reflection of the fact that all the laws of physics are the same in all reference frames. So what affects an induced current and an induced EMF? Well, it's the rate at which the external field changes. And it's the area of the wire exposed to the magnetic field. Yes, same magnitude, not the same sign. Or it's some combination of the two. If the magnetic field and the area of the loop exposed to the magnetic field don't change, no EMF is induced. So what do I mean by the area of the loop exposed to the magnetic field? And this will become clearer when I do my demo next. I'm going to do a demo on it next week. My signal generator is not working, so I have to get a new signal generator. If I take the loop of wire and I rotate it by 90 degrees relative to the magnetic field, the magnetic field is not going to penetrate, the magnetic field lines aren't going to penetrate the loop. They're not going to cross, they're not going to penetrate an area. The flux is going to be zero, and so no induced EMF. And this phenomenon was discovered independently by Michael Faraday and Joseph Henry, but Faraday gets credit for this. It's called Faraday's law. So, what is Faraday's law? This is a law, it's not something we derive, okay? Faraday's law says that the induced EMF is equal to the negative of the time rate of change of the magnetic flux through the surface enclosed by a closed loop. Okay, so let me write that on the board. The magnetic, the induced EMF is equal to minus the phi of B dt where I write this as the area vector, but let me rewrite it in more terms we are more familiar with. And so this is the time, so actually, just look at this guy. This is the flux through the surface enclosed by the loop. Okay? So if I have a loop of wire, if I want to make it go to galvanometer, I can. And I put a magnet into here. This is the loop of wire, and the surface I'm talking about is this. If I insert the magnet this way, the magnetic field is perpendicular to the loop, and then I maximize the flux. If I bring the magnet like this, the field lines won't penetrate the loop, and so I'll get no induced EMF. So this dot product is important. And when I set up my demo next week, when I get a power supply that works, you can see that. I'm going to have two loops of wire. One is going to be the source of the magnetic field, and the other one's going to be one of these with a lot of turns. And I'm just going to rotate to show you the induced voltage on an oscilloscope. And you can see that it goes from a maximum value to 0 when the loop is at 90 degrees for the magnetic field. And it's going to depend on cosine of theta, because the dot product depends on the cosine of theta, the angle between the magnetic field and the normal to the loop. Are we okay with that so far? Okay. So take a look at this circuit. I already have two circuits. I have a battery with a switch and wire wrapped around this magnet. The idea of the magnet is to enhance the magnetic field produced by the current in the wire. On the other side of the magnet, I have another coil of wire that's connected to a galvanometer. When I flip this switch, I'm going to have a time-dependent current, because the current ain't going to build up instantaneously. Your dIdt will be non-zero when I close the switch. Well, if dIdt is not zero, then, and I'm running a current through this wire, then I'm going to have a dB/dt through this loop. So I'm going to have a changing flux through this loop. And so the galvanometer will deflect. How in the world does this loop know that the current is changing on the other circuit? How does it know that? Well, it's because of the electric field. The electric field is produced, does not require a physical wire here. The electric field actually travels through space. The electric field permeates through here. The electric field is there whether or not I put this wire here. By putting this wire here in the electric field, I can force the electrons in the wire to move. So that electric field is going to exist whether or not I put the wire here. Let me skip this. We'll do this on Monday. And this kind of answered what I just said answered the question, what force is causing the charge to move in the wire? And it's the induced electric field that's causing the charge to move in the wire. And that electric field is there whether or not that wire is there. The current moves through the loop with no power source Field is created as the flux changes. And the work per unit charge done by this field is the induced EMF. So if I integrate this electric field around this loop, I will get the induced voltage. So the integral of the electric field will give you the induced voltage. This is weird because it used to be 0. So this is E induced. For static fields, that integral is 0, but for these kind of fields, it's not 0. Oops. So this is a non-conservative field. Moreover, this field has the same properties of the magnetic field. Since this integral is not 0, this means that the electric field circulates around the loop. There's an overall circulation of the electric field around the loop that I choose. Because this is not 0. And I will do this problem next time too. I don't want to do the examples right now. I'll do them in class. So what are some of the properties of this field? And I'm going to stop here. What are the properties of the induced electric field? No charges are required to create it. Kind of goes against Coulomb's law, right? It's a divergent field, just like the magnetic field. The induced field lines form closed loop, unlike static electric fields. Mathematically, they can be described as a circulating field, just like the magnetic field. They do require a time-varying field, and no physical circuit is required. And in fact, if you remember, we had a relationship This is not true anymore. Oops, sorry. Let me change these. This is not true anymore. There's actually, it turns out there's another term that has to come into play for this to be true. This relationship is not true anymore because this is true for static fields. It turns out that there has to be another term here. There will be another term here to make this work. We won't cover that in this class. Okay. All right. You guys have questions? So this is a topic where usually I do a ton of demos, but it's hard to do all the demos here. I'll try to do some demos, and I'll try to maybe send you some links to some interesting demos for this topic. I will have some on Monday, and then on Monday I'm going to do the two problems I skipped, review what I said, and then talk about emotional EMF, which basically relates to question you asked, Morgan. And it really, the question you asked really goes back and kind of answers the question, why is there a minus sign there? That minus sign is important. The minus sign in this equation is important. And so we're going to answer that next on Monday. Okay. Any questions or concerns? Okay, so I guess that's it. So you guys, if I don't see you in problem solving class, have a good weekend. And I hope I did answer all your questions. If I did, just email me.